Okay, let's dive in. Imagine for a moment running a complete, um, fully functional human brain on a computer.
Yeah, not just simulating a little bit, but the whole thing.
Exactly. It sounds completely like science fiction, doesn't it?
It absolutely does. But, the basic idea isn't totally out there. People like Alan Turing laid some groundwork, suggesting that, well, if the brain is doing computation,
And another computer could theoretically copy it.
that's the gist. It's called whole brain emulation. Think of it like running an old video game emulator on your PC. Different hardware, same game behavior.
Right, and people are actually working on this, like there's a plan.
Well, maybe not a concrete blueprint, but definitely a roadmap. We're looking at one source today that lays out sort of the three massive steps involved.
Three huge steps,
Mhm.
and it's obviously incredibly difficult.
Oh, monumentally difficult. Maybe one of the hardest things we could try to do. But the steps themselves are fascinating.
So where do we even start? Step one.
Step one is fundamentally about information. Just getting all the necessary data out of a physical brain.
All of it. What does all even mean here?
Good question. At the very least, it means mapping every single neuron and, crucially, all the connections between them, the synapses. And not just the map, but understanding how they influence each other. The dynamics.
Like a wiring diagram, but alive.
Sort of, yeah. And even for simple systems, it's tough. Take the C. elegans worm tiny thing, only 302 neurons. We've mapped its connection.
The connectome.
Exactly. But just knowing the map doesn't automatically tell you how it behaves. Researchers often have to use other methods like watching calcium ions flow, which indicates activity, to build, statistical models of function.
Okay, and human brains are, well, a bit more complex than 302 neurons and not see-through.
Massively more complex. And yeah, opacity is an issue. So the techniques are still pretty speculative. One approach is using preserved brains.
Preserved, like after death.
Yes. Companies like Nectome, for instance, they've developed methods using chemicals and cold to preserve animal brains, keeping the structure, the connections, even molecules like proteins, incredibly intact for potential later scanning.
Huh. Has that been tried on humans for this purpose?
No, not for this. And then there's the idea of scanning a living brain.
That sounds even harder.
Oh, it's highly speculative. Maybe future nanotech, tiny engineered things, or more likely, just much, much better versions of current tech like ultrasound or MRI over time.
So step one's main challenge is just getting that raw, incredibly detailed data.
That's the foundation. It's a massive hurdle in itself.
Okay. Let's say a miracle happens, we get the perfect scan. What's step two?
Step two, converting that mountain of raw scan data into a working computer model, a program.
Right, the emulation part. How big a mountain are we talking?
Estimates are around 100 trillion synapses in a human brain. You cannot possibly process that data manually, and it has to be automated. We're talking serious AI involvement.
AI to piece together the images, build the 3D map, that sort of thing.
Yes, and more. AI would likely need to interpret the physical features in the scan, the shape of a synapse, maybe, and infer its behavior, its rules, based on neuroscience knowledge.
So it's not just mapping, it's interpreting function from structure.
Exactly. And the model needs to learn, to change, like a real brain. So you need data about timing, signal interactions, neurotransmitters. Yeah. It's incredibly complex.
Turning a static map into a dynamic learning simulation.
Precisely. It's a huge interpretation challenge. And automation, probably AI, is the only way to even attempt it.
Okay. Data gathered, data interpreted into a program. Step three, running it. This sounds like the just need a huge computer part, but I bet it's not that simple.
It does require immense computing power, yes. And that might be the biggest bottleneck right now. The estimates vary wildly, though.
How wildly?
Well, if you assume computation mainly happens at the synapse when it fires, maybe you need about a quadrillion operations per second. That's roughly a top-end GPU or a small cluster today.
A quadrillion. Okay, that sounds almost doable. Ish.
But what if computation happens at a finer scale? Inside the neurons themselves, complex dendritic processing, precise spike timing, then the estimates shoot up dramatically, potentially to around a sextillion operations per second.
A sextillion. That's
about 1,000 times faster than the world's #1 supercomputer back in early 2023.
1,000 times the biggest machine on Earth. Okay, wow. That's the number.
That's the big number. But Moore's law, exponential growth. If computing keeps improving at those rates, maybe we could see that kind of power on one machine sometime in the late 2030s.
Late 2030s. That's surprisingly soon, in a way.
Relatively speaking, yeah. Other things like memory size, data transfer speed, these seem like more solvable problems on that time scale. So the sheer computational scale is the main issue today, but maybe not an insurmountable one forever.
So the 3 steps: scanning, converting, computing, getting the data, turning it into a program, running the program. Any one of those could be the killer problem.
Absolutely. And whichever step turns out to be the main bottleneck will really shape how this technology might emerge if it does. Well, if scanning is the hardest, maybe you'd have just a few scanned individuals, but potentially many emulated copies of them. If conversion is the blocker, you might have lots of scans just sitting there waiting for the AI to figure them out.
And if computing power is the limit,
Then maybe we start smaller, emulating simpler animals first, or just specific regions of a human brain, gradually scaling up as the hardware gets better.
it's definitely a long road. But it feels like progress in neuroscience and computing is sort of pushing in this direction anyway.
It does seem that way. We're learning more about the brain's structure and function, while also building more and more powerful tools to simulate complex systems. The paths seem to be converging, slowly.
So wrapping up, it's a massive, if we actually manage to overcome all these hurdles, scan a brain, translate it, and switch on the first whole brain emulation, what does that actually mean for us, for humanity? Could that really lead to a new kind of human?
That's the profound question, isn't it? What does it mean if consciousness or identity can be run on a different substrate? It's definitely something to keep thinking about as this field evolves.